Hi, everyone. Welcome back. Today, we're going to be talking about something, well, a continuation of the same sort of theme, which is we're going to be talking about how to use quantum singular value transformation in order to, and linear combination of unitaries in order to really be able to build a Taylor series expansion for time evolution operator that is the solution to the Schrodinger equation. So specifically, what we're going to be looking at is how to simulate physical systems on a quantum computer. And so let me just get this started. So the basic idea, the Schrodinger equation, basically what this ends up doing is in quantum mechanics, this ends up describing the equation of motion for some quantum mechanical system. So the basic idea is that, we've got some quantum state for a quantum system. That's at some initial time. Now that quantum state's going to evolve over time to some final quantum state that will denote psi of t. And we'd like to be able to really find a compact way of solving for the quantum state that we would see at some later time t, given the initial quantum system and some other object. This additional object is known as the system Hamiltonian. And the Hamiltonian H satisfies the following properties. It's a matrix that's in 2 to the n by 2 to the n. It's Hermitian, by which I mean that H dagger is equal to H. Okay, and so those are two of the main properties, but we're going to assume something a little bit different. In our context, we're going to end up assuming that it is the sum over alpha sub j, u sub j, where each of these alpha sub j's are greater than or equal to 0, like we usually end up doing. Okay, so this assumption that the Hamiltonian is the sum of unitaries, again, this is completely natural, believe it or not, because of the fact that Pauli operators form a unitary operator basis that we can use to describe everything. And in fact, actually most physical systems that people are interested in simulating, such as systems in chemistry, materials, spin systems, and more, end up naturally actually having a compact representation in this basis, where the number of terms, let's say we're going from 0 to m-1, in all of these applications is in Pauli of n, meaning that it's just some polynomial function of the number of qubits that the system is acting on. So these are this is the definition of the Hamiltonian. And now the Schrodinger equation is a differential equation that governs what the quantum state is at a later time. And it's given by I d psi of t by dt is equal to h psi of t. Okay. Further, we can actually write the solution to this in a nice way. Because of the fact that there's a unitary that will always end up mapping the initial state to some final state, we can always end up describing psi of t is just equal to that unitary transformation acting on psi of 0, where u of 0 is defined to be the identity. Then, if we substitute that into the Schrodinger equation, we get I d psi by dt is equal to I du by dt psi of 0. And similarly, we get h psi of t is equal to h u psi of t, or psi of 0. This allows us to actually re-express the differential equation for the vector as a differential equation for this operator. And so the Schrodinger equation for the operator can be written in the following form. Now, it's actually quite easy to verify that the solution to this differential equation is e to the negative I h t. How can we see that? Well, again, if we take a look at, you guessed it, it's Taylor series expansion, then we can write this as sum from j equals 0 to infinity of negative I h t to the j divided by j factorial. Now, because of the fact that this series for bounded h, which it is in all such cases, converges uniformly, we can differentiate inside the power series. And so the derivative with respect to t of e to the minus I h t is equal to, well, just the sum from j equals 0 to infinity of negative I h time to the j, t to the j minus 1 over j minus 1 factorial, which of course is equal to negative I h e to the negative I h t, which we can rewrite as negative I h u of t. So now, once we multiply this by I, we end up seeing, therefore, that I du by dt is equal to h u of t. Okay, so that's the solution to the differential equation. Now, we can see that it's unitary also in a number of ways. Perhaps the easiest way to end up seeing this is arises from the fact that H is a Hermitian matrix, and all Hermitian matrices are normal. And normal matrices have an eigenvalue decomposition. And furthermore, Hermitian matrices have the following property. If a matrix is Hermitian, then all eigenvalues are real. So if all eigenvalues are real, then H can be written in the form U, D, U dagger, where D is now in our real 2 to the n by 2 to the n. And so we have, therefore, that e to the negative I h t is equal to e to the negative I u d u dagger t, which is equal to u e to the negative I d t u dagger. Now, because of the fact that this is a diagonal matrix, and for any function of the diagonal matrix is just the function of, well, the diagonal elements and a 0 everywhere else. So therefore, this is equal to u e to the negative I lambda 0 t going all the way down to e to the negative I lambda 2 to the n minus 1 t with zeros everywhere else. Oh, and u dagger over here. So this is equal to that product up there. Now, just looking at this, if we take the complex, if we define this over here to be V, it's very easy to see that V times V dagger is equal to identity. Therefore, if we multiply U, V, U dagger times U, V, U dagger, we get that this is equal to U, V, U dagger, U, well, dagger, which is just U, V dagger, U dagger. So the U's cancel, the V's cancel, and the U and the U dagger cancel. And this is just equal to identity. And this implies that the matrix is unitary. Great. So now we've seen that the time evolution operator, U of t, is a unitary matrix. And so this is something that we can build on a quantum computer, consequently, because of the fact that it is unitary. So we'd really very much like to figure out a way of compiling this down. So how are we going to compile e to the minus IHT into quantum operations that we know how to deal with. And this act of compiling is often called in the literature quantum simulation. And our goal is going to be to show, to study this here and understand under what circumstances can we build this using order poly of n gates. And that's significant because the matrix that we wanted to express to begin with to describe this is on the order of 2 to the n by 2 to the n. So you can see that if we wanted to naively just implement this matrix directly, this would take exponential time on a classical computer. However, on a quantum computer, it can be done using a polynomial number of gates. So that is one of the kind of like big things about this, one of the reasons why this is so vitally important. So I should also mention that this compilation task is also one that appears in some other contexts you wouldn't suspect. This ends up showing up widely in equations for, well, in differential equations. It also ends up in some quantum linear systems algorithms work, especially before the quantum singular value transformation was discovered. And it, of course, also shows up in, as I mentioned before, chemistry, field theory, ... algorithms. So it's a very, very important primitive. But I'll just be showing the basics and how we can end up using of the singular value transformation in order to be able to carry this out. So recall what the whole idea of the singular value transformation was. What the idea is that if we have some matrix A over alpha, i.e. a block encoding of A over alpha, then what we'd like to do is we'd like to embed that inside an even higher dimensional space, but we'd like to apply some function of A over alpha divided by a normalization constant A. So we'd like to kind of embed this inside an even higher dimensional space and use that extra freedom that we get from this in order to find a good way of implementing a function. And in particular, the functions that we can end up doing naturally are polynomials. So one of the things before, when we dealt with 1 over x, right, you recall what we had to do for the linear systems algorithm is that we had an underlying function which was non-analytic like this. And what we needed to do is we needed to kind of like cut up our domain into different slices. And then once we did that, we used a polynomial approximation to this that didn't quite exactly agree with it in general. In fact, it's quite different near the origin. But outside of this range, like negative x min to 1, it ended up closely approximating it. And we needed to do something fancy through the use of Chebyshev polynomials to pull this off because of the fact that we were trying to approximate a non-analytic function that was kind of hard to get our fingers around. So the way that we're going to be doing this now is that our function actually is quite easy. It's analytic. And as I said earlier, it's uniformly convergent. So what has a uniformly convergent series. So we have e to the minus IHT. We're going to approximate this by the sum from j equals 0 to capital K of negative IHT to the j divided by j factorial. Okay. Now, if you take a look at your elementary calculus, right, one of the things that we can use in order to be able to figure out how much error we have at truncating this is Taylor's remainder theorem. There's various statements of the form for the remainder, but the one that is most useful for our purposes is the following, that the matrix norm that we end up getting of the difference between e to the minus iht minus the truncated sum, negative iht to the j over j factorial, is actually less than or equal to the next order term in the expansion. So this is the norm of h t to the j divided by j factorial, okay? But we don't have access to the norm of the Hamiltonian, not easily at least. So what we're going to do is we're going to upper bound that remainder in the following way. What we can do is we know that the sum of the Hamiltonian is defined to be the sum from j equals 0 to m minus 1, alpha sub j, u sub j. And this implies that the norm of h from a triangle inequality is less than or equal to sum over j, absolute value of j, norm of uj. But because these are unitary, all of those norms are 1. And this becomes just the sum of the absolute value of alpha j. Of course, I didn't need the absolute value, I suppose, because we already assumed that it's positive, but I guess we'll roll with it. So this is equal to alpha. So therefore, and I should put a bracket here. So therefore, this whole thing is less than or equal to alpha t to the j divided by j factorial. Okay, so that is our remainder that we end up having in our sum. So we're going to want, just like we had before, we wanted to make sure that if we approximated it using a finite order polynomial, that the deviation between a true and the actual is bounded above by epsilon. So we would like this to be less than or equal to epsilon, because this being less than or equal to epsilon guarantees that the difference between our approximation and a true is less than epsilon, because, well, that's upper bounded by something which is bounded above by epsilon as well. So that's what we're going to do. So the question is, how do we have to choose? Oh, I said j here. I really actually meant k. Did I put j up there? Yeah, I did. Really sorry about that. This should actually be k plus 1. Okay, and that should be k plus 1 factorial, and that should be a k plus 1. Okay, cool. So one of the things, it's a little bit, unfortunately, factorials are a little bit annoying to work with in many contexts, especially in something like this, because of the fact that they're not a function that has all that great asymptotic properties. So the basic thing that we're going to do with this is we're going to actually use a version of Stirling's approximation in order to be able to deal with this. And I actually realized that I probably need my notes for this. Darn. Okay, let me just shop. All right, crisis averted. I'm back from Wikipedia now with Stirling's approximation in hand. So let's go back to the write-up. All right, cool. So now using Stirling's approximation, we have that k plus 1 factorial. This is Stirling's approximation. K plus 1 factorial is greater than or equal to root 2 pi k plus 1, k plus 1 to the k plus first power, e to the negative k plus 1, e to the 1 over 12 k plus 13. And from this known result, it's pretty easy to see that this is less than or equal to k plus 1 or sorry, this is less than or equal to k plus 1 over e to the k plus 1. All right, fantastic. So therefore, what we end up with is we end up with that the error in our approximation is less than or equal to E alpha t to the k plus 1 divided by, well, k plus 1 to the k plus 1. Now, if we end up solving this, so we would like to solve this upper bound that we end up having in our expression. We want to figure out what value of k will end up setting this equal to epsilon. The solution that we get by plugging this into Mathematica is we get that k is equal to the Lambert W function with a negative sign over here of ln 1 over epsilon divided by E alpha t plus ln 1 over epsilon, all divided by W0 of ln 1 over epsilon divided by E alpha t. Okay, cool. And so just to get an idea about this, the Lambert W function is a function that's of the form, I believe it's like, W0 is like, is equal to ln of x plus order ln of x. Okay, so moral of the story is that for all intents and purposes, this function is logarithmic with some very small correction terms. So if we go through and use this asymptotic expansion in it, we can end up seeing that the epsilon scaling from this first term is going to go like, well, it'll go like a ln 1 over epsilon type contribution, which would be entirely negligible compared to this. And then you will end up getting that we get this E alpha t. So k, once we substitute that in, we end up finding that k is in O tilde log 1 over epsilon times alpha t. Okay. So that is the value of k that we're going to need in order to be able to make the error arbitrarily small. Now, the question is, what do I mean by O tilde? Now, there's O tilde. Basically, what this means is this gives scaling up to polylog factors. Okay, so this basically says that if we have any a logarithmic factor inside this that's logarithmic in the argument of O tilde, then we can drop that completely. So for example, we would end up saying log x is equal to, or say O tilde of that is equal to O tilde of log, well, actually, that's definitely true. I put the brackets in the wrong place. Okay, so let me do a better example. Let's say I have O tilde of x log squared x. Because O tilde drops logarithmic factors in it, this is equal to just O tilde of x. All right, so that's what I'm saying. You'll get some you'll get some other logarithmic factors in this when you expand it all out. But for all intents and purposes, we're just going to kind of drop and ignore it and look at just the dominant part of the scaling for simplicity. Okay, so that is how this value of k, which is the order of the polynomial that we end up needing, ends up scaling. All right, wonderful. So that's basically that. Now, what we're going to now need to do is we're now going to need to take a look at the singular value transformation. We found that K having this particular scaling will end up giving us the proper value, but we need to spend a little bit more time now figuring out, right, how to actually end up building the appropriate polynomial. So the basic idea is that we want, what function do we want to implement? Well, we want to implement function of h over alpha is equal to the sum over j, a sub j, h over alpha to the j. Okay, so then what are the a sub j's going to be? Well, the a sub j's that we need in order to match the Taylor series, which is of the form sum over j, 1 over j factorial, alpha t to the j, the various values of a j that we're, that we're, no, actually, yeah, it's gonna be that form. Various values of aj that we're going to need will be obviously equal to alpha t to the j over j factorial. And so what we'd like to be able to do is we'd like to be able to figure out what a is in this form. So a is the normalization constant that we have for the block encoding. So a here is going to be equal to the sum from j equals 0 to k of aj, which is going to be less than or equal to the sum from j equals 0 to infinity of alpha t to the j over j factorial, which again is equal to e to the alpha t. So that is our expression for this normalization constant a. And if you recall that our circuit that we had for doing this involved a oracle that we called prepa. Then we had prep going all the way down to a final prep at the bottom. And we have our target state. Then what we're going to do is, we would have a series of select operations that were like of this form, going all the way down to the final one. And then their adjoints on this side. Now we define success to be the case where all of these registers are measured to be 0. And you might, again, as always, suspect that the probability of success for that is poor. And in general, you'll be right. But we're going to want to try to improve that in order to make the probability of success actually extremely high. So basic idea behind this is that what we are going to want to do is we're going to want to, well, first off, let me define this to be LF. We showed, again, in the previous lectures, that if we have this circuit, then we have that zero tensor identity, LF, operating on zero tensor identity. This is actually just going to be equal to the matrix that we're encoding. So this will be f of h over alpha in our case, divided by this normalization constant a. We can also see that that this will end up actually giving us an expression for the success probability. We've worked this out before, but let's just go through and figure it out. The probability of success is equal to the probability of measuring all zeros on the output, given that we have a state chi, which is equal to LF acting on an initial state, 0 psi. So our probability of success then is actually just of the form, the expectation of a projector onto 0 for all of those registers at the top, tensor identity on the state, because we're not measuring the state, so we don't care about its value. And the expectation value of this projector in the state chi. And again, the reason why we do this is because a projector you can view as an operator that measures the probabilities, and it will consider the projection of any particular state on this particular value and count it towards the probability of, or count it towards the kind of like size or fraction of the state that ends up having that component. So this is why we have our probability of success expressed in that form. But we can actually express this as just 0 psi LF dagger 0 0 tensor identity LF 0 psi, which by definition, this is actually just equal to 0 psi LF dagger 0 tensor identity. And again, I'm just factoring this over here as 0 tensor identity multiplied by 0 tensor identity. So then this is equal to 0 tensor identity LF 0 psi. Okay, which when we expand this through, because of our definition here, this is actually equal to psi f of h over alpha dagger f of h over alpha acting on psi, all divided through by a squared. Now, this, of course, is unitary within air epsilon. So therefore, this is equal to 1 plus correction terms that are of order to epsilon divided by alpha squared, which is in theta 1 over a squared. So therefore, the probability of success for our nearly unitary circuit that we're taking a look at here is really dictated by this value of A, which we ended up arguing is in omega e to the minus alpha t. I guess should be a 2 here. But okay, so this lower bound on the success probability ends up looking pretty grim. But actually, it isn't necessarily as bad as it might end up looking. The reason why is despite the fact that the success probability is dying quickly as a function of alpha t, and alpha here, if you've got kind of more of a physical mindset, this you can kind of think of as like an energy scale. And in units where energy is like frequency, so it goes like 1 over time. So when the energy times the time, which is kind of like the dynamical phase that the system ends up picking up, when this starts becoming large, then the probability of success dies incredibly quickly. So we're not going to want to do this if we want to do a long time simulation. But regardless, actually, the situation isn't hopeless. The reason why is that what we can do is we can break up our evolution into a series of shorter evolutions. Okay, And so inside each of these short evolutions, we're going to basically take this duration to be t over r, and we're going to assume that there are r time slices here. Okay, so if we do that, then the probability of success then ends up going like e to the negative 2 alpha t over r. And then what we're going to want to do is the following algorithm. What we're going to want to do is we're going to want to apply oblivious amplitude amplification in each of these time steps to boost the probability of success from whatever small value it has all the way up to 1, or at least as close to 1 as we can. It turns out because our Hamiltonian or our truncation isn't precisely unitary, oblivious amplitude amplification doesn't quite work perfectly. And this leads to order epsilon errors because we're epsilon far away from being unitary for it. So when we have epsilon-sized errors, then oblivious amplitude amplification will end up, well, producing, again, order epsilon-sized errors back out of it. This result is known as robust oblivious amplitude amplification, and a full proof can be found in Childs plus Cathari and Berry, I believe, from 2016, if memory serves. But in any case, the idea is that we are going to use oblivious amplitude amplification inside each of these tiny little time slices. So we're going to want to be able to set the probability of success to actually 1/4. Now, why 1/4 again? Well, for oblivious amplitude amplification and amplitude amplification more broadly, what we had is we had a setting that geometrically ended up looking like this, where we had an angle of theta over here, and this is our initial state, and this is our target. So this is the projection of that state onto the good subspace that we want to be able to rotate up into. If this angle was over here, pi by 6, which corresponds, if you do your trig, this corresponds to that length over here being 1/2, which implies that if this section over here is length 1/2, then the probability is equal to 1/4. So if we go through the reflections geometrically, the first reflection that we do in amplitude amplification is a reflection about the x-axis. So that maps our state down here to an angle theta, and then we reflect about this axis, which causes our state to now be rotated up by an angle of 2 theta. And this angle, okay, because of the fact that the angle is pi by 6, and this is pi by 3, when we add everything together, these rotations, we get pi by 2. And therefore, if we shoot for 1/4 success probability, as we remarked on before, this will end up leading to 100% success probability after the application of amplitude amplification. Again, I recommend going back through our previous lectures on amplitude amplification if any of you are confused about this in the slightest. So in any case, this is what we want to shoot for. So let's just take the logarithm of both sides, and then we end up getting 2 alpha t over r is equal to ln of 1/4. And so therefore, we end up finding that negative 2 alpha t over ln 4 is equal to ln is equal to r, and ln 4 is actually just 2 ln 2. Sorry, this is 1/4. I did a premature optimization. And so this is, using that property, this is equal to alpha t over ln 2. Okay, cool. So what that ends up meaning is that this is a sufficient value of r to end up taking. But if we take a look back at our value of k, what we need to do is we need to end up picking k in such a way so that our total error is at most epsilon. So before, what we did is we did a individual short time step over here. And we guaranteed that our error is, when we went through it, epsilon using some value for k that ends up scaling like this. So let's call it, so what we want here is now, instead, we had, k is in order alpha t log 1 over epsilon. And this is when we were doing a complete step. Now, what we're going to want is, because we have our time steps here, and inside each of these time steps, we're going to have some error, epsilon prime, let's call it. We would like now the sum over I, epsilon I prime, like let's call this the I error. We'd like this whole thing to be equal to epsilon. So it suffices to pick epsilon I prime uniformly to be equal to epsilon over r. And then that's equivalent to picking epsilon I prime equal to epsilon ln 2 over alpha t. Okay, so this is the value of epsilon prime that we're going to plug in for the order of the polynomial that we'll need to approximate the dynamics now inside just one of these short little time slices. But also, we're going to have to adjust the value of t, right? Because it's no longer going to be t, it's now going to be a duration t over r that we're carrying out. Now, t over r, using this scaling, actually will end up going to be alpha t over r goes to ln 2. So actually, the order of the polynomial that we need, once we slice it up into these kind of like thin little bread slices across the entire evolution going from 0 to t, the value of k that we'll need per slice is actually much more modest. It is actually just going to be order ln 2, which is order 1, but this will be order log alpha t over epsilon. Okay, now, if we take a look back at our circuit, how many queries did we end up needing? Well, there are k registers here. And so then the total number of queries that we end up making is, well, we make k plus 1 queries here because we've got prep, and we've also got to build in the coefficients of the expansion. And this Oracle prepa is defined to do that. So we have k plus 1 queries here. We've got k plus 1 queries here and k here. So therefore, we've got 3k plus 2, which is in order k, queries made to these distinct objects. So the total number of queries that we end up needing per time step, or per LF, which is the block encoded function that we're taking a look at, is in order k. The number of LF needed per amplitude amplification step is order 1. Now, why is that? Because if you recall, what we had is our walk operator for Oblivious amplitude amplification is of the form negative LF identity minus twice 0, 0 tensor identity LF dagger identity minus twice 0. So this was our operator. We can see that every time we apply it, we need 2 queries. So that, therefore, since 2 is order 1, that's how many times we need to call this subroutine. Now, how many times do we need to do the walk operator? So the number of walk operators per segment that we have is 1, which we can also write as order 1. Okay, and there that we need in our total evolution, the total number of segments that we have is R. So we have that basically the total number of queries order KR, which we end up finding is in order alpha T over epsilon tilde, which of course is equal to O tilde alpha T log 1 over epsilon. All right, wonderful. So that is the final asymptotic scaling. And in fact, actually, this is all a direct and relatively, in the grand scheme of things, easy consequence from our original discussion. One of the things that I should mention is that the scaling that we see here is actually nearly optimal in time. And actually epsilon. The reason why you can end up seeing this is actually using the following type of reasoning. It's possible to choose a Hamiltonian such that the time evolution operator, e to the minus IHT, computes parity. Or at least we outlined the sketch of the proof that parity is an example of a quantum, an example of a function that a quantum computer needs order n queries to a bit oracle that yields the particular values of the bits whose parity you want to compute. That, or I should say, parity requires order omega n queries in order to be able to do this. And from this, you can conclude that if you could implement e to the minus I better than alpha queries to the types of oracles that we discussed previously, then we would beat for parity. Since that's impossible, this is optimal. Okay, so this actually is a nearly optimal quantum simulation method that follows out just immediately from the techniques that we discussed previously. I should mention it's nearly optimal because of the fact that it's a multiplicative logarithm rather than an additive logarithm. And if you're interested in looking at techniques to fix this, and if we have time, I'll spend a little bit of time talking about this later. The actual optimal scaling can be saturated using a technique known as qubitization. All right, so that's Hamiltonian simulation in a nutshell. So I hope you all enjoyed, and I'll see you next time when we're going to talk about a different set of algorithms completely. We're going to talk about the quantum Fourier transformation and how it can be used in order to be able to estimate the eigenvalues of matrices like this, which is a vitally important problem for physicists and others. Thanks a lot, and see you all next time.